I'm Brendan, and I'm really excited about types and programming languages, and I have been for a reasonable amount of time now. And I'm also really excited about kind of learning and exploring the things that academics have done in their research and applying that in industrial practice. And thankfully, in the last 2 years, I've had the opportunity and the privilege to be able to do that as my full-time job at YesLogic. And that's been really exciting and and I've really enjoyed it. So yeah, YesLogic. YesLogic is a company that's been around for quite some time now in Melbourne and for 17 years. And they create this product called Prints XML. And it basically takes the HTML and CSS and lays it out like a browser engine. We've got our own layout engine implemented in Mercury. Really interesting programming language if you get a chance to look at it. And we render that to PDF. And there's a lot of really interesting computer science problems all wrapped up in that. You wouldn't believe it, but it is. And we really enjoy our work, and it gives us a lot to work on, I guess. Part of that process of creating PDFs and doing layout and supporting the web platform is having to deal with lots and lots of these different file formats like PNGs, JPEGs, color profiles for printing, and these kind of open type and true type fonts. And now this is where I got introduced to what YesLogic does. And my boss, Michael Day, was like, "Hey, Brendan, we have this problem. There's open type and true type fonts." This was like 2 years ago. And yeah, they're really hard to parse, and it's very easy to make mistakes with them. You have buffer overflows and integer overflows and all that kind of problem. And there are implementations out there, but they're written in unsafe languages, and we don't really want to keep using those. So yeah, we have this problem. And I didn't even know what binary format, well, I'd heard of binary formats, but I didn't really know how they actually worked. And it was a little bit magic to me. But he said something else, which is really cool. He's like, I think I read this paper, like, I don't know, many years ago, and it seemed to be a way to use types and programming languages to describe these binary formats. And we could use that to describe OpenType and TrueType, and maybe in the process improve the specification around it. And that sounded really interesting, quite hard and challenging, but I thought it was pretty cool. So yeah, I said, yes, I'll take the job, crazily enough. So yes, the OpenType font file, you don't have to read this, but just know that there's a specification online by Microsoft. It's written in natural language, human language. So if you want to implement your own parser font reader for your library or font encoder, you can read this and it will tell you how to parse the font. And it has like these series of tables. Again, the details aren't important, but they'll give you like the types and the names of the fields and what's in them, and it's all really interesting. But it goes over pages and pages, hundreds of these tables, and you could write it all by hand, but it would be error-prone and prone to security vulnerabilities and that, and that's what we definitely don't want in our browser engine. So there are implementations out there in C and C++, but again, we want to improve the state of the art and make that available to other people to use. So yeah, this kind of looks like something that you could make into a programming language and then generate the parser from. So yeah, that's kind of our idea. So our goals for this, as I've kind of hinted at before, are to be declarative. So we want to say what's in the file. We don't necessarily want to say how to specifically parse the file. Like, there are a lot of ways to parse files that are very coupled to the how to parse files, things like parser combinators, where it's kind of assumed that you'll be parsing the entire thing, which is not really what we want. We want to be able to pick out parts of the font file that we need to use to lay out our text, and only that. And that kind of pops up in lots of different applications. So like if you load up an MP4 in VLC, you might just want to get the start of the file to see how big the video is, and then do the parsing of the rest of the file on the fly. So we want it to be higher assurance, so things like integer overflow that we saw in Svetlana's talk, we want to be able to potentially get that statically. And so we're investigating ways of doing that. And not making sure that we have predefined semantics around what happens if you go outside an array bounds or something like that. We want to integrate with Rust. So we don't want to make a general purpose programming language. We want to be able to use Rust to implement the logic around working with fonts, and then package that up into a library that other people can use. But it doesn't have to be specifically Rust, because we decoupled it from the specific language that we're compiling to. And we want to, this is something that we haven't quite got our heads around yet, but it is an important part. There are a lot of binary formats out there that are all implemented in weird ways. They're originally implemented in C, and there are things that you can do in C that make it tricky to specify. And so we want to have ways to kind of describe that in our format description language. And we also want to help inform future formats. And that kind of links in with the previous point. If we're showing the ugliness of what's already been specified, might have been like a quick note at the bottom of one of these tables. If we're showing what that actually looks like when you specify it, then maybe that might help people design better formats in the future. But we don't know. So yeah, I'll go through some of the prior research that we've looked at, the process of implementing this data description language, and then I'll sort of go through some lessons that I learned along the way. So yes, there has been research out there. This is just showing that there is a paper out there. You can go find it. This next 700 data description languages was the kind of initial thing that my boss saw back in 2010 that he hoped someone would implement well, but we're here implementing it ourselves. And the really cool thing about this paper is that it takes an existing data description language, PADS, and describes it in terms of this core calculus. Well, this is just an example of what it would look like. Just get the shape of it. It's got unions, it's got data structures, and based on previous information that you pass, that will affect the types that you pass later on. That's really important. And yeah, it gets translated into this kind of lower level calculus, and that's really exciting when you see that in a paper. It means that there's something well understood under there that's easier to specify. If it's all like this ad hoc stuff glued together that's hard to understand, it's less interesting potentially, to us at least. So we're excited about this. Then there's all this other work that's been done on parser formats over the years, and there's new stuff that keeps popping out every year, which is kind of exciting, but also kind of like, whoa, why am I doing this if other people are making this cool stuff? And they're doing it in theorem provers and stuff, and that can be kind of, I guess, intimidating. But once I get over that terror, like going and looking at what they're doing, it's really helpful for my work. And I'm thankful to these academics who are spending a lot of time in writing about what they've done and carefully describing what they've implemented so that it helps my work as well. So I think academics deserve a lot of praise for the work that they do, and we should support them and talk to them and keep learning from them. I think that's really important. And there are also projects out there, other data description languages that don't necessarily do all of the things that we're hoping to do with our data description language. There's this one, WAFs, from Google that is very imperative. It's like you'd write a C program, but it checks integer overflows and array bounds and stuff, which is really cool. But again, it is very tied to how you pass it, not what you're passing. Nom is similarly tied to how you pass it, but it's fast and it's in Rust. Could eventually become a target that we compile to. Kite struct is more on the declarative side of things, but it doesn't really have that basis in core theory, which we're interested in, and it doesn't do the type checking that we're interested in as well. So yeah, we've seen this, and there's more out there too. So a lot of people have tried this problem and succeeded to various levels, and we're trying our hand too. Who knows whether we'll be successful or not, but we hope so. So I'll just show an example to try and make what binary formats are a little bit more concrete. So imagine you have an image that's like got dimensions, it's 4 by 5, and a bunch of pixels. I've just got like a red ball up here, a little bit of pixel art for you. So what we want to do is translate this into a stream of data in memory. And so what we can do is we can put the length, the width and the height up front in our binary stream, and then that kind of guides the passing of the rest of the binary format. And so it will tell you expect 4 by 5 pixels later on. Now I've kind of glossed over the pixels might be declared as another binary format with red, green, blue values in them. And so you kind of nest these formats into a larger, more complicated format. This is a very simple example. It gets more complicated as you try and describe things like OpenType. But yeah, you can imagine that as just being a bunch of ones and zeros. I just mashed my keyboard a bit. But yeah, imagine that is actually showing an image. But yeah. And so we can kind of describe it, this is what we want to get to. We want to describe it as this high-level data structure, and I'll go through, some of the interesting parts of this. You can notice that there's like this width and height up front, and they're described as unsigned 32-bit integers, and they're in big endian form, which is, it's kind of like, there's almost like another binary format just to describe these unsigned integers, but yeah, I won't go into that. But the interesting thing that I want you to notice here is that the values that are in the former fields in the struct actually change the type that you're expecting later on. So there's kind of this dependency between the width and the height, and the height, and there's kind of this type level expression here, which is kind of interesting. And it's an array of pixels, so yeah. That's kind of interesting. It pops up actually in dependent type theory, which is an interesting fact as well. Yeah, we want to take advantage of that mirroring between some of the theory that people have been working on for decades and actually using this in a practical application. And so we can, then what we want to get to is compiling this down into Rust code. It's a lot of code, but it's generated code. In fact, we're handwriting this at the moment just to get a feel for what we want to generate. But yeah, you can see that we've got these dependencies they're turned into dynamic code. We're generating it from the data types. It's almost like Haskell generics, if you're familiar with that, but you don't have to be. Or shapeless in Scala. And you could imagine we could generate different things from this same data type. So we could potentially generate stuff for a theorem prover if we wanted to check that our data formats are sound or not. The other interesting thing is that we've lost some of the strong typing in the compilation to Rust. Like now there's no link between the width and the height in the fields of this image and the pixels later on. In the future, maybe we could compile this to a dependently typed language or even have our data description language embedded in a dependently typed programming language. But at the moment, they're not. The dependently typed programming languages that we have right now don't really compile to efficient code. And if you do want efficient code from a dependently typed programming language, you need to do a lot of work to translate that down to a lower level. And this is kind of a pragmatic decision that we've made. We're just going to compile to Rust. But in the future, it might be really cool to see if we can get closer to this ideal of we're just programming with our dependent types. So yeah, the process of doing this, it's been a long process. Like back in 2014, Mike was doing this before my time at YesLogic. Michael was building a prototype on his Christmas holidays. He was trying to, we'd already implemented, I think, multiple passes of OpenType by hand, and Mike didn't want to do it again. And so he took that paper from 2010 and implemented a proof of concept in Mercury. And that wasn't doing any type checking. It was just reading off interpreting the binary format description and kind of dumping out the results of the file. And so that showed that the idea was kind of a little bit sound. It was useful. And then I came along and took my hazy rememberings of this book called Types and Programming Languages and thought, yeah, I'll try and do this. And ended up running into some walls because it was actually really hard. I thought I'd been done in like 6 months, but turns out not. So I was trying to do the software engineering thing where you like do a vertical slice and you like add a feature and then you add another feature and then you add another feature and you're constantly compiling down to Rust. And that's kind of good if you know where you're going, but I ended up implementing myself into a corner and I couldn't get my head around this evaluation of expressions at the type level. And so I was very fortunate that I could talk to Mike and say, oh, can I go back and learn a bit more and try again? And so that's what I did. Meanwhile, my colleague Mark was experimenting in Prolog with some experimental type systems, trying to get his head around DDC, that dependently typed data description calculus, which was very helpful to me later on because it gave a bit more understanding. But yeah, I found this paper called A Tutorial Implementation of a Dependently Typed Lambda Calculus, and that was really helpful. It's a tutorial that shows how to implement dependent types in Haskell. And I could do this process of porting that from Haskell into Rust. And this is a process that I've found really helpful over the years, taking something that's in one language and then translating it into another, because I can learn a bit more about that language that I don't necessarily know all that well, and I can also learn about the ideas as well as I do that porting. And so I made this project called LambdaPy. It eventually turned out into my own another project, but yeah, I won't go into that. The thing I was struggling with here was variable binding, which is surprisingly challenging. I don't know if anyone's implemented a programming language before, but kind of relating the variables and the parameters to the stuff in the body of your functions is actually quite challenging, especially when you want to interpret these things in an evaluator and compare the equalities between two functions. I found it challenging and hard to understand, and that's what limited my ability to implement type systems in the past. But because it was a job, I had to learn it, and it took a few months. I went down this road. I looked at different ways I could do variable binding. I didn't really understand how that tutorial was doing variable binding. It seemed kind of magical to me. And so I was trying other options that might work a bit more with Rust. And so that led me to this paper called Unbound, and it's this library in Haskell that you can describe the binding structure on your abstract syntax tree and generate the variable binding code so you don't have to look at it. But I then got feedback. Like, I was going on. This was a breadth-first thing. It was like I tried to see what I could do, and then I tried to adapt it to the stuff that I wanted to do because I didn't want to rewrite it. I wanted to just get on with parsing binary formats. And I had this thing public, and people were saying, oh, it's really hard to understand this variable binding stuff. And I was finding when I was implementing the data description language the second time around, I was running into issues with my variable binding code. And so I ended up just asking for help on Twitter. And because things were public, I could then get feedback from some of the researchers that I'd started following and talking to on Twitter. And that led me to this thing called semantic type checking. So a lot of thanks to John Sterling and Danny Gratzner, who I think are over in the States. I can't remember which university. But yeah, they pointed me to this way of type checking, which I don't have time to go through in depth. But it's a way of getting around all the issues with variable binding that I was having before. And that was really helpful. And there's an example implementation in OCaml. And again, I did the porting process from OCaml to Rust, and I learned it a little bit more in depth, and that was really helpful for me. And so we eventually started implementing some of the parsing by hand in prints to get a feel for what we wanted to compile. And now I'm currently working on the hopefully final version of the data description language in the end-to-end form again. So now that I know where I'm going, I can do the vertical slices, and that makes me feel a lot better. But yeah, I couldn't do that without having seen the landscape and invested the time in learning. And so it's been a really helpful experience for me. So yeah, it's public. So you can go and check out YesLogic/DDL. We don't know a good name yet. Still thinking about that. But if you have any ideas, let me know. But we've kind of gone a little bit backwards, so we don't have all of the dependent structures just yet, but I can see how that's going to all fall into place as we go forward. And I've also been really careful to show some of the prior experiments that we've done. So all of this stuff that you see is all going to be in that repository. So you can see all our mistakes and learnings along the way, which I think is really important. You know, it's important to show the stuff that didn't work out necessarily. I've also posted links to references and stuff. So yeah, lessons. Bidirectional type checking that you heard from Ambrose earlier on today is really useful. That's what I learned in the tutorial implementation of lambda calculus. I think it's actually a lot easier to learn bidirectional type checking than going down the route of learning Hindley-Milner type inference to begin with. So I'd highly recommend you searching for that. I've got a few links to references on the DDL repository and in the slideshow. Yeah, so that's the paper. Reaching out to researchers is really handy. It both helps them feel better about their work, because sometimes they feel like they're stuck in the ivory tower. It's not just like us versus them in the ivory tower. They feel lonely too. So reaching out to them and saying, your work is important, is really nice. So they like to feel valued just as much as we do. And you can get useful tips if you're struggling. Semantic type checking, still a little bit magical to me, but it works amazingly. It was an idea that popped up in like 1996 or something, and it's taken a while for even the researchers to get an idea that this is a good idea. And having a pointer to that and being explained why that was useful was really helpful to me. And so there's this repository by Danny Gratzner, which is confusingly named NBE for MLTT. Who would know that this is actually really, really useful? But it is. So yes, I would recommend, if you're interested in this stuff, try porting it to the language of your choice, like Scala or Haskell or Clojure, and see how it works. Because I think that's a great way of learning, trying to implement things. And yeah, it's okay to rewrite things. Like, I was stuck in this mode of I just need to push through and like bodge it until it works, but sometimes taking a step back. And if you have the time and can pay the money, you can, it's good to have the opportunity to rewrite things once in a while. I put a star on there, you know. Don't rewrite the world, but if you have the chance, rewrite a little bit. And here's a whole bunch of links to things. I will try and make these slides available. They're not available right now, but follow me on Twitter and yeah, I'll try and post them. Yeah. So yes, our DDL is this one little step. It's like a little bit in our effort to make programming a little bit more sane for ourselves and hopefully for other people. But there's a lot of people doing a whole bunch of other work, more than I could fit on this slide. But I hope that in the future we're kind of going towards this magical place up here. And if we're all moving in the right direction, I think, maybe we have a chance. So yeah, that's me and that's my talk. Any questions?
Is it easy to say how close you are to parsing these binary formats? And follow up, how about a binary format that includes like a virtual machine that helps you parse further things in that format? So the format specifies follow the next things in the binary format, execute on this machine to actually generate the in-memory structure.
That sounds really cool. Okay, first part of the question, how close are we? I have example binary formats in the repository. We're working up to a stage where we can kind of swap out bits of our current implementation to use the data description language. I've had to do a lot of work in the past month to kind of get us to that stage, but we're getting there. And so I guess the idea is that we want to have it integrated into our current system because we're implementing a font shaping engine ourselves, which is another crazy endeavor. You can talk to my colleagues Adrian and Wes about that. But yeah, in order to make this viable, we need to get it integrated and used. But it's becoming hard to maintain that parsing code because it is just so vast and large. So it's coming time that we integrate it, and yeah. Virtual machine stuff, that sounds really cool. I have no idea how to do that, but maybe we could do that. The thing I'm excited about with dependent types is it kind of blurs the line between compilation and runtime stuff. There are problems to do with that in making it compile well and efficiently, but maybe it could be done using like a virtual machine. I'd like to chat to you about it. Yeah. Any other questions?
Hey, great talk. Just a really quick one. What kind of is your roadmap for different backends for DDL?
So we're just focused on Rust at the moment. We are also compiling documentation, and we want to have like a GraphViz output to kind of give you kind of an overview of how the types link together. And so potentially, based on the work that I've done in the Rust version, hopefully it's easier to implement your own backend, and maybe we could have some documentation to help people do so. So, yeah, not in the foreseeable future, but yes. We're trying to provide a well-documented, well-tested foundation that other people could potentially use. Any other questions? Cool.
Thank you, Brendan.